Okay. All right, perhaps we shall get started then. It's my great pleasure to introduce Bob Coecke, and it's probably appropriate that I introduce him because I'm probably one of the few people here who can properly pronounce his surname. So Bob Coecke. We know each other since we were students in Brussels, since we were probably something like 18 or so.
You were maybe 17 because you came to the university early.
Yes, when I came, but I'm 1 year older anyway. So after that, after doing his undergrad studies, I think he started in engineering, civil engineering, but then he decided to quit because I recall you telling me that something.
I took an internship and I had to sort of walk into the real world. I wasn't really so good.
Okay, so after that, he continued his mathematics and physics in Brussels. Then he did his PhD over there. We shared the same supervisor.
And office and cigars.
Office and cigars, yes. Then you started moving a little bit around. You were in Montreal for a little while. Imperial College. And then finally ending up with Stamsel Abramsky with Oxford, where he eventually became a professor. Now an emeritus professor because he decided to quit in 2020, I think.
Yeah.
And he's now the chief scientist at Quantinuum, which I understand is the largest quantum computing company on the planet at this stage.
Yes.
I'll let Shay do the acknowledgement of country.
I'm of the Barongo clan of the Dark Nation, and I've been invited to welcome you to Wallamado, country, the traditional country of the Dark, where Wallamado campus resides. And I'd like to pay my respects to elders past and present, and I also want to say that having this, doing these acknowledgements of country, although they're sort of standard, they're still very important and meaningful to me and my community. So thank you.
Yes, thank you. It's as I was saying earlier to Ross and Steve, it's for me a little bit like coming to Mecca, and you'll understand why during my talk. So I assume, I know there is at least one physicist in the room. You're the person who's not in Adelaide, because at the moment there is this Australian Institute of Physics annual conference going on in Adelaide, and all the physicists are there. I gave a plenary talk there. It was just pretty much the same talk as this one, by the way. So I gave this yesterday to physicists. So I mean, that's also a point. Like this talk I usually give to physicists or computer science or mathematicians or philosophers or whatever, to be honest, businessmen, even businessmen. So that's how Australian category theory has evolved now. Anyway, so the story I'm going to tell today is about, like, I mean, on the left-hand side, like you see all these childish looking pictures and stuff like that, which you would find in a children's cartoon book or something like that. And so I'm going to explain what they are. And then I'm also going to explain how they led us to quantum natural language processing, which is a thing which is real. So we have been doing like natural language processing, like things like question answering with quantum computers, thanks to these pictures on the left. So that's what I'm going to talk about today. I'm going to go very slow, so please interrupt me whenever. Tomorrow morning I give another talk at 11, and then I sort of zoom in a little bit more in details. So, but this is going to be like very, very high level and stuff like that. And it's not like a talk, okay, here's the problem, here is the solution. So it doesn't matter if I don't get to the end. It really doesn't matter. It's just like a bunch of stuff. Let's put it like that. Okay. Oh, okay. Oh, I've got this. Is this a stick to move? Yeah, I think. Up. Is this the one?
It's down there.
They're not sort of moving. Can I can use the screen. Okay. Oh no, this is not moving. Nothing is moving.
Oh, because it's not selected, I think.
Ah, okay. Oh, now it works.
So I think up is previous and then down is left.
It's not really moving, but okay, it doesn't matter.
Oh.
It works here. Doesn't
Okay.
matter. Doesn't matter. Does the laser work? Oh, the laser works. Yeah, that's okay. So I'll say a little bit more detail where I'm now. So for 20 years I was in Oxford. Like for 30 years of that I was a professor in the computer science department. But I was a professor of quantum foundations, which is kind of a funny story. I was the first professor of quantum foundations in the world, which in the light of the recent Nobel Prize, like the Nobel Prize of this year, is kind of an important thing. Quantum foundations was like a very marginal topic, which was looked down on by a big part of the community, just like, as some of you know, category theory at some points in time. It was looked down on the community, and that's not true anymore. Same is not true anymore for quantum foundations. Then there was like sort of consolidated by this year's Nobel Prize. So I was actually the first professor of quantum foundations in the world. And the only reason this was possible is because I was in the computer science department and not in the physics department. Okay, that's a sociological comment. So we had a big group there, as some of you know. I know you probably recognize many people here, like Jamie Vickery is in that picture, Stefano Goglioso in this picture. Is Alex Kissinger in this one? I don't know. Like, but anyway, we had this very big group, Samson Bramsky and I, at Oxford, which was mainly sort of a quantum/category theory group, as I think many people here know. Then I resigned from Oxford and I became chief scientist at a British quantum computing software company called Cambridge Quantum in 2021. In 2022, that ended. And the reason that ended is because we actually happened to merge with part of the big American company Honeywell. So Honeywell, you probably know, if you go to some sort of a thermostat here, you will see Honeywell and stuff like that. They do control systems, and they were actually building quantum computers somewhere in a corner. So that part of Honeywell split up and joined with us. And so we became Quantinuum, and that's now, like Frankie said, the largest quantum computing company in the world. We're some 500 people now. Anyway, so but besides my global role, I also got my own group in Oxford still, so I'm still in Oxford. And we focus on what's called compositional intelligence. So I think people here who've heard about category theory, you know, that's a theory of composition and stuff like that. So this is our logo. You see my t-shirt here. We got t-shirts and stuff. So this is the C of composition. The C of composition. This is the I of intelligence, because we do some sort of a compositional form of AI, so to say. It's a Q because it's sort of quantum inspired as well. And then very unfortunately, it happens to look like a skull. I'm sorry. Right? Okay. I'm gonna start this story very long ago. Well, not that long ago, but a little bit long ago, like almost 100 years ago, with John von Neumann. So John von Neumann is known, for example, for game theory. He's the father of game theory. He's also the father of the modern computer architecture, like whatever computer you have. It's a von Neumann computer, basically. He built the architecture, not a computational model, because that was Turing, but the architecture, that was von Neumann. And he's also famous, well, maybe not less famous for than that sort of stuff, for actually being the father of the formalism of quantum mechanics. So he's the father of using Hilbert space and linear algebra and that stuff for quantum mechanics. He published a book in 1932, putting like Hilbert space forward as the way to go with quantum mechanics. And then something very unique happens in science, because usually when somebody does something, people have a hard time admitting that they're wrong about something. So von Neumann, he wasn't wrong about anything, but in 1935, he said, I would like to make a confession which may seem immoral. I do not believe absolutely in Hilbert space no more. So he basically denounced Hilbert space, which was his brainchild, as the formalism in which you should do quantum mechanics. That's what he denounced, what he put forward. And then a big part of his career was basically looking for alternatives to Hilbert space. And if you look around you now, you won't find any of them. So nothing of what he did ultimately was successful in becoming an alternative formalism for quantum mechanics, as opposed, not even for doing some local small stuff. It's just nowhere. It's honestly nowhere. One thing he came up with together with Gary Birkhoff, because this was actually from a letter to Gary Birkhoff, like the lattice theoretician. One thing he came up with, Gary Birkhoff, is called quantum logic, and that's actually used in cognitive science and stuff like that, but not in physics at all. So that's kind of, I mean, me and Frank, we did our PhDs on that stuff. And then I was unemployed. So he was pretty much dead and straight. On the other hand, so anyway, that's what went on. On the other hand, while doing all that stuff, trying to come up with new formulas of quantum mechanics, he invented a whole bunch of new mathematics, which is now very established. So like he made major contributions to lattice theory, invented von Neumann algebras and all of that sort of stuff. So he wasn't a wasted time and a wasted cause and all of that. Okay, now, so that said, so von Neumann then said, okay, we need to find a new formalism of quantum mechanics. And the way we are going to do that is by really deeply understanding quantum mechanics and what's really key about it, what sort of the foundational concepts and differences with the world in which we live about it. And starting from that, we can start to mathematize that idea and come up with a new formalism. And so von Neumann's focus was very much on the concept of measurement. What happens in quantum mechanics when you observe or measure something? You may know that if you do that, you actually disturb the system. And that causes, of course, a completely different mathematical description than, say, propositional logic a la Aristotle. And this is actually what he initially focused on, how logic changes when you actually, whenever you observe or look at something, it moves or it gets disturbed. So his focus was totally on measurement. And for the remainder of the century, and even now, pretty much everybody followed von Neumann, thinking that the thing in quantum mechanics which you need to understand to deeply understand quantum mechanics is measurement. So pretty much everybody followed it in that idea. So here we got Erwin Schrodinger. So Erwin Schrodinger is known for his cat and for his equation, stuff like that. And then in the same year as von Neumann sort of denounced Hilbert space, 1935, von Neumann, Schrodinger wrote something else, and which is much closer to the heart of all the category theoreticians which are sitting here. So what von Neumann, Schrodinger wrote is, and he was talking about the idea of like composing systems in quantum mechanics. So you bring two systems together in quantum mechanics, and what happens then is that they lose their identity. They lose what they are. So usually if you want to describe two systems, you say, okay, you describe the first system and then you describe the second system, and now I've described both. So what happens in quantum mechanics is you bring them together, that new states emerge, new wholeness things can emerge, to the extent, I'll give you an example, that a very interesting thing emerges, but then when you look at the individual systems, they're just noise. That's something that happens in quantum mechanics. And this is called entanglement. If you've heard about the word entanglement, Bell state, EPR state. So it's a joint state of a system, which is very useful, which is very interesting, and which leaves the systems as individuals as pure noise. So that's entanglement. And so that's a special kind of composition which happens in quantum mechanics. And Schrodinger said, I would not call that one, but rather the characteristic trait of quantum mechanics. So he had a completely different idea than von Neumann. And I mean, arguing against von Neumann about mathematics is not a thing you do. And so nobody cared about what Schrodinger was saying because he was just a stupid physicist. Let's put it, I'm joking now, I'm a physicist. But yeah, everybody ignored, and Schrodinger and everybody follows von Neumann because on this statement, except Sampson and I. In 2004, we published a paper, a categorical semantics of quantum protocols. And to some extent, this could be seen as realizing Schrodinger's view from the perspective of monoidal category theory. Because what is monoidal category? So who is not a category theoretician here? There's quite a few people, right? Okay, so I'm going to teach you what monoidal categories are. Not like these people teach you, like I teach. So monoidal categories is a theory where you just give names to a few things. So you got stuff, and then you got a symbol which says, okay, now I've got two things. And then you talk about the processes between maybe two things here and two things there. So what process can we have from two things here and two things there? And that's really what a monoidal category is. Right, Steve? So that's a monoidal category. And so this was basically the way to articulate Schrodinger's view, because the basic constructor or symbol in the theory is just composing systems. That's what it was about. And then you need to pick out like a certain type of monoidal category, because this covers pretty much everything. Whenever you're cooking in your kitchen, it's a monoidal category. Whenever you do anything, it's a monoidal category, because it's just about like putting things together and then doing stuff with it. That's a monoidal category. There's nothing more to it. So not everything is quantum. So we need to come up with a special kind of monoidal category to basically say, okay, these are our quantum monoidal categories. And so we did that, and we did this in this paper, and then we showed a few quantum phenomena derived in category theory. I'll show later some. And we actually didn't have to do much work to get there, because other people had already done the work. So on the left, that's Jean Benabou, who came up with the concept of monoidal categories. On the right is somebody called Max Kelly. He happens to be a local here, or used to be a local here at least. He's the father of the category theory here. Am I right? Father of category theory here in Australia, which actually is called Australian category theory. The kind of category theory I'm going to talk about here is called Australian category, period. And it's all from Sydney, from here, I think initially University of Sydney and now mostly Macquarie. Yeah? Am I right? So Max Kelly came up with a kind of category theory, was almost spot on what we needed. We just need to add something which we call a dagger. I mean, I'm not a violent person, but yeah, there's skulls, there's daggers, you know, like. So we had to add a dagger to it, and the dagger was actually for the people who know mathematics here to accommodate complex numbers. That's why we needed the dagger. So, but yeah, we pretty much, the category theory was available, so it was just a matter of like applying it to quantum mechanics to actually show that even at that very abstract level, you can actually derive very useful things, and I'll do some for you later. Okay, unfortunately, Australian category theory wasn't the sort of a bread and butter of most people in the world. Especially physicists were a little bit reluctant to get into that stuff. And like if you try to, for example, read Kelly's paper on compact closed categories, I mean, it's not easy. Let's put it like that. Not even for somebody who knows category theory. It's not easy. So there are better ways to do, well, not better ways, but maybe more popular ways to do things. And this is Roger Penrose. And when Roger Penrose was an undergraduate student, okay, let me just say something about Roger Penrose. So he's a person who actually worked closely together with Escher. So a lot of the Escher paintings were a result from Penrose's, also Penrose's father, by the way, talking to Escher. And he also got a Nobel Prize for black holes. When was this? 2020? Penrose, I can't remember. 2020 or something? Something like that. But another thing Penrose did was, I mean, when he was an undergraduate student and he had to learn relativity. In relativity theory, you've got all these symbols, sort of. Like, let me see if I can get this to work. Yeah, here. So you have all these things, they call this Einstein notation and stuff like that, with all these indexes and stuff like that. And he hated it. And he kind of realized that it could as well represent these tensors just with pictures and wires and stuff like that. So the wires corresponding to the indices, the big thing correspond to the big symbol in the middle. They now call this Penrose notation. So he did this as a student. And he basically Huh?
Max Kelly was looking over his shoulder during the lecture when he was diagnosed.
Seriously? They were together? I didn't know that. Okay, that's nice. That's nice to hear. Oh, that's where he got it from. That's cool, actually. So yeah, but I mean, nothing happened. Penrose never really published, and I think at some point it appeared in some appendix of a paper or something like that, but it was not something people took attention for. But then, a few years later, this is André Joal and Ross Street sitting here. They basically kind of proved that these Penrose pictures and monoidal categories, I mean, they weren't talking about braided monoidal categories, were the same thing. They were basically the same thing in the suitable way of saying the same. Okay, that's cool. So we don't actually need to use the monoidal categories explicitly. We can actually start using these pictures to do stuff in their own right. So in 2005, I wrote a paper called Kindergarten Quantum Mechanics. And this is basically exactly the same paper as the paper with Samson Abramsky. Like we did exactly the same thing. We showed like that with these structures of Kelly's monoidal categories plus a dagger, you could derive a lot of quantum stuff, but we did it entirely in pictures there, rather than using the symbolic notation. And of course, we could only do a few things in quantum mechanics, things like teleportation and some other things. And then I posed the question, can we do all of quantum mechanics in terms of pictures? All of it, which was a very ambitious project at the time, and nobody believed me. Everybody was like mocking me, like all the physicists said, this is all complete nonsense. You're never going to get there. It just makes no sense. So fast forward. Fast forward 13 years, I think. Yeah. Oh, no. Okay. I'm going to explain something. Oh, wow. That's good. Some maths. So just to give you a feel about what reasoning with pictures mean. So here you see sort of a bent wire. Here you see a bent wire. And the person just yanks it into a straight wire. It's a thing you can do with a wire. It just doesn't change anything. It's still the same wire. But if you think of this particular equation in categorical logic, it's an instance of the deduction theorem, a generalization of the deduction theorem from a certain kind of logic to another kind of logic. There's a PhD thesis about that from 2005, I think, by Ross Duncan, who did the categorical logic of this equation. But a simple thing, and you'll see later how it works, like yanking a wire is actually like a logical deduction. It's an incredibly powerful thing. And then now, I mean, I think most of you will have heard about linear algebra. So what you see here is on the left-hand side is a box of a certain shape. And you have to think as the bottom as the input and the top of the output. So what we do here is we wire the input into an output. We wire the output into an input. And that actually, if you think of the box as a matrix, is a realization of a transpose. This is really equivalent to the transpose in linear algebra. And then now I'm going to show you like the power of the yanking. So if you yank this box, then the box rotates 180 degrees. And so this tells us now, okay, we got a different notation for a transpose. We can also just represent it by like rotating it 180 degrees. So that's the kind of logic of wires. That's how we can do things. And everything in linear algebra, like unitarity, inner products, traces, can all be represented in this very, very simple picture. So most basic operations in linear algebra can be represented in all these very simple pictures. And so that's very nice and elegant and simple. And it's incredible that it's not wider used than it is at the moment. It's just ridiculous that people are not using this more wide. In linear algebra in general, I mean, in linear algebra in general. Anyway, 13 years later, after I stated the goal to make quantum mechanics entirely in terms of pictures, Alex Kissinger and I wrote this book. So Alex Kissinger pretty much took over my role at Oxford University now. So this is a course we have been teaching for eight years now, or maybe more even, at computer science as the quantum computing course of computer science department. And it's a full-blown course which teaches everything you need to know about quantum computing and quantum foundations. And it's entirely presented in pictures, in the sort of pictures which I was aiming for, like all based in terms of monoidal categories. So there's nothing more than monoidal categories going on in pictures. Now the book is quite thick because we are responsible teachers and we're not going to sort of send these people off with their pictures in a world where nobody understands these pictures, so that they can actually not get a job anywhere else except in picture land, which at the time was not so big. So it's we explain how from the pictures you can derive Hilbert space and stuff like that. So it takes a lot of space, and that's why it's quite a big book. And it's definitely not kindergarten quantum mechanics. The level of the book is university level. It's university level book. We wrote it's from 2017. Now we move 5 years later. Okay, you can show it around to everybody. So now there is a new book. I mean, this copy is a week old. It was actually the first copies. I've got an email yesterday that there is now thousands of them printed and they're going to start to be distributed. And from a little bit after Christmas, you can buy them on Amazon or something like that. I think next week there is already Kindle available. The book is called Quantum in Pictures. And this book, effectively, you don't need to have any math background. It's supposed to be accessible for everybody who has the will to get into it. But there is no math sort of background needed whatsoever, and it's written in a way that it's supposed to be quite easy. So you can't buy it at the moment yet. I think it's listed in Amazon at the moment, but you can't buy it yet. So I wrote this with Stefano Goggioso, who is also now in computer science faculty. So that's actually like a step further than the previous book, But I mean, if you want to become a professional in this stuff, then I would say you first read that one and then you read the big one, because that's probably the way to go. So because kids actually don't read anymore, we actually video the entire book in lectures, and these lectures will all be gradually put out on YouTube, available for everybody. So the book is quite cheap. It's published by my company, Continuum. You can see it on the side there, Continuum on top. And the reason is they wanted to keep it cheap on purpose, because there's something going on, like there's a good chance that technology is going to evolve over the next 10 years, much and much more towards quantum, and to avoid all the troubles like which happened with AI, that these people were just being given like the free way to do whatever they want with all the problems we know now with all the big AI companies. The idea is to try to first democratize quantum reasoning and stuff like that before the actual tech revolution happens, that people at least know what's happening, and that the responsible people can also make care that things are kept responsible. So that's why we are publishing it. You can have a look. It's a really good quality and it's quite cheap. It's less than £10. Well, it's very good quality paper and a nice color and stuff like that. So we're not making any money with it. We're not making any money with it. Okay, so I'll very briefly, I go through it just to give you a very vague idea of what's going on in there. Not indeed. Tomorrow, I'm going to give much more details about all these things. So the idea is we've got a theory of wires and boxes. You have to think of a wire as a thing where particles, quantum particles, or whatever live, where they live. They travel there. This can be quantum particles. You can also think about electricity. You could think about water, whatever. It's like a pipe where stuff lives. It's a very simple idea. And then a box is something that transforms that stuff. So maybe you got electricity getting in, and this is transformer, and then you get another kind of electricity going out, or so on, or these are quantum particles, and then something happens to the quantum particles, you change their state, and then they come out. So that's the idea of wires and boxes. So you can plug these things together, obviously, and make more complex networks of them. And things become really interesting at this point if you start to make new boxes from things you actually really understand well, like wires. So what I'm doing here is I take these previous equations, or like equation, I wasn't even talking about equations, like you take a wire which is bent, and then you yank it, because it's then still the same wire. And now I'm going to start interpreting the left-hand side in a different way. I'm saying the cup-shaped wire at the bottom is actually a box. I'm going to declare it to be a box. And so what kind of box is it? It's a box which doesn't have any inputs, right? You don't see any inputs there. It has two outputs. So it's a box with no inputs and two outputs. Then you see this cap-shaped box at the top. It has two inputs and no outputs. So it's a box with two inputs and no outputs. So the one at the bottom we're going to call state. It's really like the state in computer science or a state in physics, and it basically means I'm creating two particles. I'm creating two particles, and because they are created because of this cup-shaped wire, they are special. These very special particles, and they are what physicists call maximally entangled, or EPR state, or Bell state, or something like that. They're very important. This is the thing which the Nobel Prize this year was given for that particular cup thing. That's what it was about, really. And then the thing on top, you have to think of, it's like the creation of the state upside down. It's like the question, are you an entangled state? Are you a Bell state? So it's dual. One produces, you can think of the bottom as the proposition, and on the top as the question. Are you in this state? And now suddenly, when you start reading this diagram in physical terms, it becomes a completely different, non-trivial thing. So on the left-hand side, we got an open wire, means you can stick something in it. So something can go in it, it's an open wire, it's an opening. And then you create two particles in this very special state, in this Bell state. Then you act with your test or your question on the first one and the first one of the Bell state. And then the third one just goes through. So it's a non-trivial process. It's a non-trivial process, but the equation now says it's the same as doing nothing. It's all this stuff, all this effort is the same as doing nothing. That's what this equation says. And we're going to later see why it's important, why it is an important equation. So we were talking about the transpose before, as if it was something like you rotate 180 degrees. So now you say, if I take such a cup-shaped wire, and I take a box and I just slide it along the band below, you see it's the same as actually it becoming the transpose because it rotates 180 degrees, right? Okay. All we said now, all of thought you now is enough to derive the physical concept of quantum teleportation. Quantum teleportation is a very important thing. It was invented in 1992. Am I right? 1992? Something like that, something along these lines. Yeah, 1992. It's really nothing more than this in first order. What it is like, I mean, here I draw, that's a badly drawn galaxy. In the book, they're much nicer. They're little planets. You've seen them. It's much nicer and much more elegant. So it's a badly drawn galaxy. And so you see there is this cup shape. Well, let me see if I can shine on it. Yeah, you got this little cup here at the bottom. It means some sort of pair of entangled particles is created. One of these particles goes to this side, say that's Alice is there. One of the particles go to the other side, say Bob is there. Here, Alice has a certain state, which is labeled by this diamond, because it has no input, it's a state. And she wants to give it to Bob. She wants to give it to Bob. Now, in the presence of this cup state, all she needs to do is do this cap test or cap effect or cap question on this diamond state and the particle she has from the entangled state. Because now we can just push this box all along this wire to the other side. We can just push it to the other side. Because the fact that it doesn't have an input, it doesn't matter. You can just slide along this wire anyway. And then the output is just, like a trivial wire. For the category theoreticians, this is the identity. This is the identity, your monoidal unit there. So you don't, the monoidal unit, you don't draw. So there's just nothing. And okay, so that's quantum teleportation. This is something that took physicists 60 years to invent after von Neumann's book, and 6 very, very smart physicists who have been decorated with other prizes for coming up with this. So take that into account. This simple, trivial thing, which I explained to you, took physicists 60 years to discover. Okay. There is, for the physicists here, I'll just be fair, there is a qualification that actually this thing on top you can't do with certainty, and then there is a little bit of extra stuff, but it's equally trivial, and I'll explain this tomorrow in a more detailed account. I just want to go a little bit further here. But this is basically what, when people did teleportation in the lab, which was Zeilinger who got the Nobel Prize, was the first one to do this. This is effectively what they did. This is what they did, nothing more. Okay, so now these wires alone, they're not good enough to capture all of quantum mechanics. You can't substitute quantum mechanics with wires. That would sound a little bit too silly, right? You can't do that. And so instead, we substituted with spiders, which actually sounds more silly even, right? Okay, what is a spider? So to understand what spider is, we need to understand what a wire is. A wire is a thing. What is a wire? So a wire is a thing with 2 endpoints. Right? That's what a wire is. A wire has 2 endpoints. And as category theoreticians, like there's a bunch of them in the room, they don't want to say what a thing is, but they want to say what a thing is by actually composing it with other stuff. That's what category theoreticians do. And computer scientists would say we characterize things by their behavior. So how they interact with other stuff. And so what's about the wire concerning composition or their behavior? Well, if you connect 2 wires together, you get a new wire. So it's kind of boring. A wire is quite a boring thing. Like if you connect 2 wires together, you get a new wire. So basically a spider, okay, here is one, it's very friendly. It's the same thing. So if you connect 2 spiders together, you get a new spider. That's it. So it's exactly the same. I mean, here you see 1 wire. It doesn't matter whether there is 1 wire between them, whatever number of wires between them, they just connect into a new spider. Now, it's not as boring as wires, because here you see a spider with 2 5 legs. Here you see one with 4 legs, and here you see one now with 7 legs. So we got a new spider out of all spiders. So it's a little bit more interesting. And I mean, I'm not going to say anything. I'm going to say later something about these spiders, but I don't want to break up my story now of the simple thing. But there are some very deep theorems about these spiders, but I'm not going to say them now. We'll get back to them soon. So we need not just one kind of spider, we need two kinds of spiders. And what happens if like one kind of spider meets with another kind of spider is the following: they both hit each other. They both give them like a hook to each other, boom, and they hit so hard that their arms fly away and they fall off. So whenever spiders are connected by two legs, these legs fall off. That's the rule about spiders. Why are these things useful? And now I'm going to dive straight into quantum computing. So this is a quantum circuit. How should you think of this as a quantum circuit? This is something you can find in a quantum computer. So these vertical wires you have to think of like as qubits or something you're acting upon. These vertical wires are something like qubits. So we got 3 qubits here, 3 qubits at t time 0. So these are 3 qubits at time 0. And then at time 1, we do something to it. And then at time 2, we do something to it. And then at time 3, we do something to it. What do we do to it? So what we do to it is like the result of composing these two spiders together. Now, I know mathematicians will be very confused by this horizontal wire, but it just means that this is the same as this. It doesn't matter how you put it, so you just put it like that. And as it happens to be the case, for the typical choice of these spiders, which we do in quantum mechanics, this is what's called a CNOT gate. It's called a controlled NOT gate. So controlled NOT gate is a thing that if it gets 0 here, then it will do nothing. If it gets a 1 here, then it will negate whatever bit is there. That's what a controlled NOT does. So it's a very standard logical operation, and you can prove that for a particular choice of this spider and a particular choice of this spider, you always get controlled NOT gate. So we got a circuit here with 3 controlled NOT gates. Now, quantum computers now are quite small today. They're quite small. And so you want to, whatever program you stick on them, you want to make as small as possible. You want to make as small as possible and compressed. So the question is, can we make this simpler? Can we make this one simpler? Let's see. So what we see here is we got a red dot here and a red dot there, and they're connected. So let me go a bit back. So these spiders fuse together, right? Whether it's red or green, it doesn't matter. We got 3 green dots here, so they're going to fuse together too. Let's do it. Boom. We just did it. We see like 2 wires between red and green. They go away. You remember? This one. They go away. And now we see like a red dot with just 1 input and output. Yeah, that's just a wire. That's just a wire. So we were able to simplify this circuit to this circuit, just using these simple spider rules. Now, this is a very stupid example. This is a very totally trivial example. But as it turns out to be the case, this has become a very important problem for current quantum computers to just simplify these circuits. And what I just showed you is the state of the art. There is no better way to do it. This is the state of the art to compress quantum circuits, or it's part of the state of the art. You do a little bit extra things, but this is part of the state of the art. So the best quantum compilers now all do this based on this calculus, based on these diagrams. So this is a piece of technology, what I just showed you, modern technology. Okay. Let's move a bit forward. I'm not going to spend too much time on this now. Tomorrow I'm going to give much more detail about this. But so this year's Nobel Prize is about something called quantum non-locality. Quantum non-locality means that if you take quantum systems and you lay them out in space, in physical space, far apart, using these cups, for example, that there is no way you can come up with a model, a classical probabilistic model, that doesn't signal faster than light, that can actually simulate whatever happens there. So there is something genuinely different going on with quantum in space-time than with classical stuff. And the way you prove that, and I'll do this in more detail tomorrow, is this is like a purely quantum scenario. When you see these double lines at the bottom, it means we're dealing with quantum systems. When you see the single lines at the top, it means we're dealing with classical systems. So you do a bunch of quantum stuff, then you do some classical computing. I'm not going to explain this in detail because I want to say some other stuff too today. Let me check my time. When did I start? Started at 4, right? Okay. So yeah, so I want to say something else in the remaining time. So I get in much more detail in this tomorrow. So this is the expression of the idea I just told you, that you can have a classical representation. You see everything is single wires. I explain tomorrow what this is exactly, not today. And then you can show, just using the algebra I showed you before, that this thing can never be equal to this thing. And that's basically the content of the Nobel Prize of this year, and that people show this in the lab. And you can do this entirely with this sort of compositional graphical language. Something we are doing now, an experiment in collaboration with IBM is, and that's actually the very reason I actually started writing this book in the first place. I wrote this book because we wanted to teach teenagers and younger people quantum mechanics using this stuff, and then put them up against Oxford University students who have gotten a normal quantum computing course. And then ask them the same questions. Ask them exactly the same questions and see who wins. And we know in advance who's going to win because I've been testing it, like secretly. But now we're doing this experiment large scale, like I say, in collaboration with IBM, because they've got a big network of teenagers and stuff like that going on. And so that's what we're using. And you can expect results in 3-4 months or something like that. But so we're going to show that using Australian category theory, children can outperform Oxford University students. Just to put it in the right phrasing here. Okay. So everything we have been talking about is from a paper with Ross Duncan from 2007, which we and then there's bigger versions after that from something we call ZX calculus. We call this ZX calculus. Z and X are actually the names of the two colors of spiders. They correspond in physics with what's called the Z and the X observables. That's what they correspond with. And when we came out with this stuff, it was well received in computer science communities. It was well received in maths communities, but the mainstream quantum computing people, they were a bit skeptical about this. How are you going to ever beat with category theory or beat with these diagrams, do anything useful that we can't do just with our normal ways? And it's like, nah, you'll never come up with something like that. Okay. Anyway, like just to give another historical note, all the maths, a lot of the maths we use there, so especially the maths of what the spider is, that's coming from a paper by Aurelio Carboni and Bob Walters, the paper on Frobenius algebras from 1980, am I right? 1980-ish. And then the interaction rules of the spiders was actually made very clear, and which we by Steve Leck in a paper composing props. So all the maths basically, I mean, Bob was from here again, Steve was from here. So again, the idea of a spider was invented here. If you think it's a silly idea, blame those people, blame him. Anyway, so like I was saying, people weren't taking it seriously for a long time in quantum computing. These are all the companies involved in quantum who are now using these spiders. So, and I'm learning new ones every week. So these are all companies, take a time to look at it. IBM is really big on this stuff, really big. They really believe this is the way to teach quantum and all of that. They're really big on it. They're using it for lots of stuff, practical stuff as well as educational stuff. You see things like BBC there, JP Morgan, whatever. There's a lot of really big companies there. So they're all using this stuff now. They're all using this stuff. And there's going to be more and more and more. So for example, I was giving a plenary talk yesterday at this Australian Institute of Physics thing. It's like there's like more than 1,000 people in the audience, a very big talk. The head of PsyQuantum was talking before. There's a company like PsyQuantum, which is another very, very big quantum computing company. They're doing photonic quantum computing. And I mean, he in his talk had a slide which said like ZX calculus is immensely useful. It's the only thing we use. So this stuff is now basically becoming mainstream. My whole life, I mean, see, look at that guy's face there, look at his dress, look at me. My whole life I've been trying to stay underground, and the last illusion of being anything like underground just went away yesterday. So I'm a boring mainstream now. Anyway, so why is this so powerful? And this is a serious piece of maths which actually doesn't trace back to Australian category theory in any way. So these guys, a lot of them are former PhD students of me. They showed that the ZX calculus, and I didn't give the full presentation here, I'll do that tomorrow, is complete. What does it mean? Let me first say it's universal, meaning every matrix can be written down in terms of spiders. There's something extra you have to do. You have to decorate them with a group, which you get for free for like a generalized abstract nonsense, like we say. So you can write down anything in linear algebra using these spiders with decorations, decorated spiders. I didn't introduce them here. I'll talk about them tomorrow. Decorated spiders allow you to write everything down in every matrix down, everything in linear algebra. But what this result is about is that any equation you can derive using Hilbert space and linear algebra, you can use with this diagram. You can derive with these diagrams. It's a complete system. And that's why it's so powerful. It's a complete system. It's a complete logical axiomatization of a Hilbert space. So it really realizes to some extent, or to all extent, whatever von Neumann was looking for. An alternative to the Hilbert space formula, which in this case is much more intuitive, as we will show with our educational experiments, and which now some companies, like the optical quantum companies, have adopted as a substitute for Hilbert space for pragmatic reasons. It just worked better. It just worked better. Right. Okay. So what time is it? I'm not going to say anything about this slide. This is just a blog post I wrote, which, I mean, if you want to read, is about like my perception of the Nobel Prize and how this is related to all the stuff I'm talking about here. Because anyway, this is Jim Lambeck. Okay, somebody else. I mean, some people know here. So who's Jim Lambeck? He's also a very important person in category theory, but he's kind of a broad person. He did a lot of different stuff. And one of the things he did in 1956, he wrote a paper, The Mathematics of Sentence Structure. So what was this about? This was a piece of algebra in which he showed, which allows you to show when a sentence is grammatically correct. I'll tell you a little bit about this works, but basically this was like a piece of maths that tells you, that allows you to compute when a sentence is grammatically correct. I mean, people probably know the name Chomsky, but like Lambeck did some deep foundational work, mathematical foundational work in this area. And so I was in Montreal in 2005, and I was presenting my teleportation stuff with wires there very proudly. And then Lambeck was in the audience and asleep, because I don't know, some people here probably gave talks in the Montreal category theory seminar, and the experience is you got a bunch of whole people sleeping there. And then they wake up and then they start to ask very interesting questions. Have you had that? That's what it is. They're all sleeping and then they start asking questions. So Jim was there lying asleep, and then I was talking about my picture, and they quickly woke up. I said, "Hey, Bob, this is grammar." I said, "No, Jim, this is physics. Go back to sleep." No, Bob, this is grammar. Really, really, really. And he was right, because the last sort of formalism for grammar he came up with, which was in 1999 or something, and he called these pre-groups, was exactly the same in categorical terms as Kelly's compact closed categories. It was the same thing. They were compact closed categories, exactly the stuff we used for quantum. So he was right. He immediately recognized, yeah, this is the same as my grammatical structures. 3 years, I mean, I didn't take much notice. I thought this was like a freak coincidence or something like that. So 3 years later, I had a bunch of colleagues at Oxford University. There was Marnouche Chaderzadeh, who actually knew this stuff of Lambeck. I didn't really know it. I just knew it was the same categories. And she knew it because Lambeck had asked her to work out his new theory of pre-groups in the case of Persian, for a specific case of Persian, the language Persian. And she's from Iran. So I'll give you an idea on what these pre-groups are to some extent. So basically these grammatical gadgets are stuff where you actually identify some primitive types, like here, this is noun type. Noun type is a thing which can exist in its own right. You can say a word as an answer to a question. A sentence is a thing, of course, which can exist in its own right. And then a thing like a transitive verb is not something that can exist in its own right, because it needs a subject and an object. And the way you indicate this in this calculi, I mean, this is, for example, you take the sentence type and say, I'm a transitive verb and I want to be a sentence. But in order to become a sentence, I need the noun on the left and I need the noun on the right, which we indicate by these -1s. It's like we need to, and then, for example, if you take a transitive verb, we stick a noun on the right, we stick a noun on the left, they cancel out and you get a sentence. And that's how these things work, and they work for any sentence, right? Now, the important thing for us here is that this little calculation, the canceling out of this noun and its inverse, and the canceling out of this noun and its inverse, can be represented by a diagram where you basically take this cup-shaped wire, which represents the idea of these two annihilating each other. And then the sentence types goes through. Does it make sense? Do you see that this calculation can be represented by this diagram? Yeah, makes sense? Yeah. Remember that, just remember this diagram here. And remember that this diagram is a witness of grammaticality of noun, transitive verb, noun. That's all you have to remember. So, okay, so somebody else who was in Oxford was Steve Clark. And he was a proper linguist, actually, but a kind of more modern type of language. So now you have all these things like GPT-3 and all these language embeddings, and what they do is they represent meanings as vectors. They represent meanings as vectors. And he was doing this in 2006, 2007, before deep learning and all that. He was nowhere near like the sort of prominent thing. Now it was a purely academic discipline, and they were trying to see what can we do if we represent meaning by vectors. For example, things they said, this is when you compute the inner product, you give some idea on how similar words are, stuff like that. That's what they were doing. But okay, we got here a theory of grammar. We got a theory of meaning. And we as humans, we're able to combine them. If you know the meanings of the word, and I tell you a sentence and it's grammatically correct, you conceive the meaning of that sentence as a whole. That's something we as humans do, because we can understand sentences we never heard before, provided we understand the meaning of the words and the grammatical structure. We just it gives us something, which is the meaning of a sentence. And then these people working with vectors, they said, okay, can we combine the vectors for words with this grammatical structure to get something that produces a vector which is representative for the meaning of a sentence? And then we can do stuff with that. And nobody had done that before. There was no theory for that. And so once Steve asked me this question, I mean, I knew the answer. Well, I mean, Jim gave it to me. Jim gave me the answer. Because these diagrams, they represent grammar, and what flows in the wire are vectors, because it's theory about quantum stuff. And quantum stuff is represented by vector standardly. So we had a formalism here, in which we could combine meaning of words with grammatical structure. So we wrote this paper together, and it's now a big area of research. It became clearly, now it goes under the name of Coecke, name I didn't come up with and just hate, but that's the name it goes under. So we came up with that, and I'll show you how it works. Let me check the time again, because I definitely want to get to a certain. Okay, I'm going to speed up. So I know I'm going to skip some stuff. So basically, what you've got on top are the meanings of the words. So you've got to think of this as a vector. This box is a vector. Vector Alice, vector H, vector Bob. And then what you got on the bottom is something which makes them interact. It's a linear map. This is like our states in quantum mechanics, or cup state and stuff like that, or Bell state. So there are things which live in linear algebra. And when you and it's quite intuitive, because you see Alice is fed into H, Bob is fed into H, and then this interaction spits out the meaning of a sentence. It's quite intuitive the way it works. I'm going to skip that. I'm going to talk about that tomorrow. Yeah. Just saying like that the spiders also have a role. Yeah, your spiders also have a role there. We use them to model things like relative pronouns. And then you can make inner products. So, okay, let me speed up, because I do want to make the punchline of this talk. I'm nowhere near the punchline, by the way. So the thing was, like, I told to my colleagues, like, don't mention quantum. Because if people are going to say we solve a problem in linguistics by quantum, they're going to call us crackpots. But we just used the formalism which was out there and which seems to solve the problem. That's all. But okay, the media didn't agree. They started to call us quantum linguists and blah, blah, blah. We did a lot of experiments, by the way, with that stuff, and we outperformed everything. We were better than everything with this new theory. We were better than anything around. Much better, much better. We had a big problem. We didn't scale. So it only worked like in small scale because the tensors or boxes became too big on classical computers. So this is Richard Feynman. So Richard Feynman, another Nobel Prize winner, said in 1980, if you got any theory, be it chemistry, be it materials, where you use quantum mechanical description, the only way you're going to do your computations is on a quantum computer, because a classical computer just can't cope with it, because everything is going to scale exponentially. So you have to go to quantum computers, and that's what's happening now. That's quantum computing is so big, and people are putting chemistry on it and stuff like that. Chemistry is the biggest application of quantum computing, but we were working with a quantum model. So that's why we couldn't scale. He didn't want to live on a classical computer. He wanted to live on a quantum computer. That was, well, I mean, we're still doing it on classical computer, but really naturally wants to live on a quantum computer. So then in 2016, Will Zheng, who's a former PhD student of me, and now is the head of quantum at Goldman Sachs. So these banks have now all quantum groups and stuff like that. We wrote this paper, and basically we checked, if you're going to stick this stuff on a quantum computer, do we get any typical quantum advantage algorithmically? Do things speed up? computations, and the answer was yes for any standard task in natural language processing, we got computational advantage. In 2020, early 2020, we were able to actually do natural language processing on actual quantum computers. So these were IBM machines, IBM quantum computers, and we did actual natural language. We did some question answering with them. So I'm still in shock about that fact that we were able to do that. I'd never believed to see anything like that in my life, but we actually did that. We actually did that. Then we did it bigger, and now you can do it. You can just go home and do it yourself. So basically what we did is we took all our software, all our tools we had built to realize this in practice. We made it very clean, very nice, a lot of documentation and stuff like that, and we put it out there open source for anybody to use and for anybody to manipulate and all that. And you just need to read this paper to understand what to do with it. So see the name, Lambeck? See the name, Lambeck? So that's how we knew call the thing Lambeck with a Q. And so this is software which is out there for everybody to use. And for example, this is a team from IBM, and they recently put out a paper where they actually tried to scale up much more than we have been doing. This is another team of IBM who actually used our stuff to start generating language. And the interesting thing is these two teams at IBM didn't know of each other, they were doing it. So it's really something which is taking off, this quantum natural language processing. And if you want to actually read in detail what I'm talking about here, because I'm just rushing through the slides, IBM wrote a really nice blog. So this is Coecke, this is IBM, an introduction to quantum natural language processing, and they very nicely explain all the stuff I'm being saying here in a way much better than we have ever written it, or more accessible, in a way more accessible than we have ever written it. Okay, and now this is the fun stuff I want to definitely get to. So what we did then is we took out the linguistic grammar out of Lambeck. I mean, you would have loved this Lambeck. Hey, Lambeck, I'm taking the linguistic grammar out of you. People who know Lambeck would realize he would actually love that too. And then we put instead a musical grammar into Lambeck. So we changed that. There are things called musical grammars. And so we took the linguistic grammar out, we put the musical grammar in. So it suddenly had a means to generate music with a quantum computer. Okay, music with a quantum computer. So we did this. Software is available, so you can do it yourself. It's called Quanthoven. So small IBM quantum computers are available for everybody. So you can basically use them, and you can use the software with small quantum computers. Everybody can just do this now. So we made a few songs, and then we ended up #1 in some classical charts. Like Bob Cigarbus, you remember I was talking about Frankie and me just smoking in the office all the time and stuff like that. So yeah, Bob Cigarbus ended up #1 in some classical charts. This is Brian Eno, who is actually taking a lot of interest in our like Quanthoven. And so when I'm back, we're going to go to his studio and we're going to see what we can do together. Do you know Brian Eno? Anybody knows Brian Eno? Yeah. I wasn't there because this was last week and I was here in Australia. These are collaborators of me. Inside Lambeck. So what happens inside Lambeck? That's going to be the last thing I say. Inside Lambeck, you got basically, we start with a linguistic thing here. So this is like Alice hates Bob. And we're going to start to deform it. First of all, we sort of simplify the representation of the verb by sticking some spiders into there, some Frobenius algebras. We pull them down. Now we need to get a quantum circuit, because quantum computers only understand quantum circuits. So we pull out some more spiders. Like that. Now we got CNOT gates. Quantum computers are small, so we just use all the elasticity of these diagrams to go from 4 systems to 3 systems. And now we just parameterize this. We parameterize these boxes with some more spiders. And this is really what goes into the quantum computer. And then there is some machine learning going on to actually learn these variables and stuff like that. I mean, this you can all read in this IBM blog if you're interested in that. It's very easy going, this IBM blog. They explain all of this stuff. That's what's going on into Lambeck. And then in the last 1 or 2 minutes, I want to. So there's a weird thing going on here. We changed language, which is one word after another, into a 2-dimensional thing, which is a circuit. Like just like symbolic category through string diagrams is turned into a two-dimensional representation. So we took language and we turned it into a two-dimensional representation. And then we studied this two-dimensional representation of language. We actually made it canonical. We actually produced an algorithm. I'm going to go a bit fast forward. Me with these guys, we produced an algorithm. So we took, this is a language with a certain grammatical structure. It doesn't matter whether you understand. And now I'm just going to do duk, 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 duk. You get a circuit. This is an algorithm. This is an algorithm for all of English. So it turns all of English, every text, not just sentences, text into a circuit. And then we looked at other languages. So this is the circuit for an English sentence. And then we looked at other languages like French, and then things with intrinsically different grammatical structures because of different word orderings in different languages, they all became the same. We've done it for Urdu too. Every language just becomes the same in this two-dimensional circuit representation. And then we looked at different ways of writing things down, many small sentences, one long sentence, they all became the same. So in the process of going to these circuits, we seem to have come up with like a representation of language which is really universal and which really seems to capture the meaning under all languages. So, I mean, this is very recent stuff. You're not going to find this in any paper. Papers aren't out yet, but it's a pretty cool thing, I think. And I'll end it here. Brrr. Yeah, we're all musicians, by the way. We're all musicians. Yeah, blah, blah, blah. We're all musicians. There we go. End of story.
All right, thanks for the most entertaining talk. I assume there will be some questions.
Yeah.
So the only concept of natural language processing itself is coming and with the sort of generation of language, it's becoming very easy to sort of replicate very human sounding paragraphs and things. And this is already being used like as the ChatGPT, which is come out.
Sure.
It's being used to sort of, I mean, it's being used by like my friends to write their assignments for it. I was sort of wondering sort of how you think it's going to sort of impact education, it's going to change a lot.
Educate, well, I mean, what do you mean, like for cheating?
Yeah, like, how schools can sort of adapt to all this stuff.
I mean, this language stuff is not specifically focused on education. The diagrams initially for quantum, that's focused on education. And you could actually teach grammar in this way, which is actually also much easier than the usual way. The main upshot of this new theory of language is a thing where all these GPTs and these chat GPTs completely fail at, is that they only consider short connections between words. They can't deal with long connections between meanings, while we have a theory of meaning which deals with entire big text. So there is, how should you say this? There's much more understanding going on here. There's much more understanding going on, and I mean, I was at the Australian Institute of Machine Learning 2 days ago, and their only focus is like trying to go beyond today's machine learning. It's a very big institute, biggest entity in Australia in AI and machine learning. It's in Adelaide. And their only focus, and I think they're doing the right thing, is going beyond these big language models and trying to bring some more reasoning into it. And they're doing a lot of stuff. They're trying to bring causality and stuff like that. But when they hear this thing, they said, okay, this is what we're going to do now. So that was one of the big options of my visit here with this. In education, I mean, I think that it's not going to be long. I mean, I've got a good team behind me because the book is published by our company, and they're really focusing on bringing this diagram really early on in education, like in undergrad education. And I think it's more than doing maths differently. I think there's more about it than doing maths differently. It's getting a different view on the world, not a view on the world where you think of things how they are made up, where you think of things how they interact with each other, how they relate to each other. And I think this will also make better politicians, to be honest, than the ones we have now. Does that make sense?
Yeah, I have two questions. So one is a physics question. You mentioned applications with quantum mechanics, and also you mentioned general relativity applications of the same thing. Just wondering, because I know that there are conjectures about emergent gravity to do with entanglement metrics. whether the pictures that you get in the two different contexts are at least superficially similar when you look at the pictures.
So something actually what you say, I didn't say, but it's true. So you can use the diagrams also to formulate the relativity theory and like covariance and stuff like that. And I've got now a big quantum gravity project as well with Carlo Rovelli. And we're really trying to see how this idea that this diagram appeal both to quantum and to relativity maybe can guide us towards a new approach to quantum gravity. I think that was the goal of your question, right?
Yeah, that was. That's great. The other one, the linguistics, they gave an example of languages that you were able to find these models to. There are lots of languages that are kind of counterexamples in some sense, the Chomsky's generative grammar hypothesis. So indigenous languages to South America and Australia as well. I was wondering if you were able to model.
So okay, I've got two answers there. The first thing is like language is not an exact science. You can't treat it as pure mathematics for starters. So there will never be something that applies to every language. A lot of it does, a lot of it. Then the other thing to say is Chomsky's generative grammar is a very rigid formalism. It's much more rigid. I mean, this is a little bit like Chomsky's generative grammar, the pictures I showed here, which I didn't explain at all. This is like a generative grammar. It's like you got little generators and you generate your sentence. And this thing is a very rigid thing, and a lot of things can go wrong and stuff like that, or different. But the point is, when you move to these things, everything just becomes the same. This is what Chomsky wanted, but never got. Chomsky had this, and this is still something which was different in all languages and stuff like that. All languages become the same. So, I mean, I can't say more because it is so fresh and so new, but clearly there is something going on, which is a little bit what his ideal was. And also a part of his universality of language and stuff like that was the idea that it was sort of inherent to humans, it was sort of baked into our brains. But when I mean, I didn't talk about it today, that would be another talk, but these things are much closer to how nature works, rather than to our brain works or that language is specific to us. So I think this is something more inherent to nature, which is much inherent to animals as us. But it is the core of language. Now, the thing is, we can't speak this. Okay, read this. You can't, because it's two-dimensional. You can only say one word after another. So what we as humans did is, we took this thing, which is actually the stuff which is going on out there and in our brain, and we had to force it on a line. Just for the people who know category theory, like bifunctoriality is trivial in 2 dimensions. And then when you want to go on one line, you have to come up with an equation for it. This is the same thing. We had to come up with a lot of equations for putting language on one line. And the French, of course, made different decisions than the English. And made different decisions than the other. So that caused all these different word orderings and stuff like that. And that's where all these big complex differences come from. And some people used word orderings. Other people, like Latin, they used like stuff at the end of words to make these sort of bureaucratic decisions. And in other languages, other decisions were made. But that's kind of the most I can say about this now. But I think this solves a lot of these problems.
Have you looked at like the relationship between this stuff and information theory?
I mean, this is not quantitative information theory. This is theory of information flow. And of course, you at some point you want to put a quantitative layer on top of this, and this would be some new kind of information theory, which is not just information theory. Like many theories in engineering, people want to reduce everything to a number, but a number doesn't tell you the story. And sometimes you want to actually do something more than reducing everything to a number, if you understand what I mean. But yeah, you could define an information theory on top of this. You understand what I mean?
Yeah.
There's an online question from Rakesh. Does this formalism just simplifies understanding the evolution of quantum system, or does it also provide insights into quantum measurements?
Yes. Yes. I mean, this was not part of this talk. Like I'm going to talk about that tomorrow. Actually, quantum measurement becomes a totally trivial thing which emerges from composition of systems. Schrodinger was right. Composition of systems is more fundamental than quantum measurement. And tomorrow I'm going to show this. And but I mean, not just quantum. I would say not just quantum measurement, but the reason it's used in quantum computing companies now so broadly is because it actually teaches you something about quantum mechanics, which normal formalism doesn't do. You have to compare this to, there was a time that people computed computers in machine code. I mean, they thought, okay, you can do everything in machine code. Of course, you're not gonna design an operating system for your iPhone in machine code. You're not gonna do that. And in the same way, this language teaches you things which machine code wouldn't. It teaches you, for example, the example I gave was teleportation. It tells you teleportation is completely trivial, which Hilbert space doesn't. And it took 60 years to come up with it. So that sort of stuff it teaches you, yeah.
Any more questions? Thanks for the fun talk. So related to this generalization to gravity and maybe even field theory or something like that, can you describe infinite dimensional limit space?
So yeah,
you know, toy is still possible. It's just
yeah. So there's a bunch of papers by Stefano, my co-author of the book, where he has been extending all of this to infinite dimensions. Yeah.
So you still have a completeness theorem?
No, we have completeness theorem since 2 weeks for all finite dimensions. Not yet infinite. They said the completeness for everything beyond qubits is 3 weeks old.
Other questions? At least we should thank Bob again, I think.
Thank you.
I understand that there will be some sort of a continuation of the event, so
Okay, that's good.
next